All right, let's dive into today's main topic, AVL tree. First, I'm going to talk about the motivation of why we are studying AVL trees. In the last lectures, we saw that we implemented binary search tree last time, and we try to feed a sequence of numbers in an increasing order in this way. And when we did this, the binary search tree constructed looked like this: 1, 2, 3, 4, 5, blah, blah, blah. And it just looked like normal linked list. And because this tree is not balanced, searching for a number in this way, in this structure, took O n rather than the expected time, log n. So in this class, today's lecture, we want to resolve this issue. And what is an AVL tree? An AVL tree is a high balance binary search tree. In the previous lecture, we talked about binary search tree, where the left nodes, left subtree, the values of left subtree is smaller than the root, this node, and the right subtree has values that are larger than the root. And this property is maintained for all nodes. However, our binary search tree does not balance its height. So its height could look like this. And this could lead inefficiency. And we're going to resolve this issue using an AVL tree by balancing the height. And what does it mean by height balanced? The height balanced means the difference between heights of left and right subtrees cannot exceed 1 for all nodes. This is the definition of height balanced. And we count the height of the empty subtree as -1. And while we are defining the height of the empty subtree as -1, it will be clearer when we implement AVL tree. And this AVL tree is named after the inventors George Adelson Velsky and Evgeny Landis, AVL. And can you guys guess which one is an AVL tree between these two trees? This is a very easy question. In this case, this node, let's have a look at this node. The height difference between the left part and the right part is just 1. So for this node, the AVL attribute property is satisfied. And what about this node? The maximum height of the left part is 3, whereas the depth of the right part is 1. So the difference is 2, so larger than 1. Therefore, this is not an AVL tree because the height difference between the left part and the right part is larger than 1. In this case, for every node, the height difference between the left part and the right part is not larger than 1. Therefore, we can call this an AVL tree. Furthermore, as you can see here, the left items have values less than the root, and the right values are larger than the root value. So it is both binary search tree and AVL tree because it is height balanced. So that was the definition of an AVL tree. And how are we going to calculate the height of AVL trees? Before we talk about that, let's think about this problem first. What is the smallest number of nodes that an Abel tree with height h can have? Can you guess n0, n1, n2, and n3? I'll give you some seconds. Think about this and send me your answers. So here, height 0 means there is just one level. Height 1 means there are 2 levels. And height 2 means there are 3 levels. And try to guess the smallest number of nodes, nh, that an Abel tree with height h can have. I'll give you about 1 minute and think about it and send your answers to me. All right, thank you for sharing your answers. Let's have a look at these numbers together. Okay, so in the case of n0, it is going to be 1 because we have one level and the smallest number of nodes we need to have is just one node like this. And when we can have 2 levels, then the minimum number of nodes we need to have is 2. Because at the first level, we need to have the root, and we don't have to have right or left children, either of them, because the height difference between the left one and the right one is not larger than 1. So the minimum number of nodes when we have height 1 or level 2, 2 levels, the minimum number of nodes we need to have is 2. And in the case of H2, we need to have 3 levels like this, and to balance each node so that the height difference between left and right does not exceed 1 is using this configuration. So in this way, we need to have at least 4 nodes. And in the case of H3, the answer is 7. So other than this configuration, there is no other way to construct an Abel tree. Okay. So any questions up to this point? All right, let's move on. So we saw the smallest number of nodes in H, and we're going to use this notion to calculate the computational complexity of an Abel tree. And I claimed that NH can be represented in this recurrence equation. So why is this so? Because we need to have at least one root. We need to have at least one node. So we need to have +1 here. And the left child should be an avial tree. And the right child also need to be an avial tree. And the maximum difference between those two can be, the maximum height difference can be 1. So the left one, let's say, is height n-1 avial tree, and the right one is height h-2 avial tree. So this is why we can represent NH in this recurrence equation. So one of the subtrees, say the left subtree, must be an avial tree of height h-1 because the current avial tree is height h. Thus, it has at least n h-1 nodes. And the other subtree, say the right subtree, has height either h-1 or h-2. And here we want to calculate the minimum number of nodes. So we are taking h-2. Therefore, it has at least n h-2 nodes. In conclusion, NH can be represented in this recurrence equation. And this one corresponds to the root node. And we are going to solve this recurrence equation. Since clearly NH-1 is larger than or equal to NH-2, we can say we're just putting this equation, this relation to this equation, then NH is larger than 2 times NH-2. And solving this equation, we can say NH is larger than or equal to 2 to the power of H divided by 2. Okay, so if you solve this one, you can get this equation. And we know that N0 is 1. So using these two facts, you can come to this conclusion, which implies we take log here on the both sides, then log n is larger than h divided by 2. So here n signifies the number of nodes in the tree, in any avial tree. And we saw that NH is the minimum or smallest number of nodes. So n should be larger than or equal to NH. And we can come up with this equation. And when we solve this, log n is larger than or equal to h divided by 2. And here, we could say h, the height of an avial tree, is smaller than 2 times log n. So you just swap the right and left position, then you could say h is smaller than 2 times log n. So it's a simple math. So we could say the time complexity of an avial tree is log n, because the height is smaller than 2 times log n. So this is how we calculate the time complexity of an avial tree. And another thing we could see here is that this recurrence equation looks like Fibonacci numbers. And in fact, this one is Fibonacci h plus 3 minus 1. And we just claimed that this NH is Fibonacci number h plus 3 minus 1. And we are going to use mathematical induction to prove this relation. And when h is 0 and h is 1, f0 and f1 is 0 and 1. And when we insert these numbers, we could easily verify that this relation holds. And for general n, h, we could put this relation here. Then we could easily verify that these numbers, these equations, really reduces to this relation. This is not that complicated. And for more detailed analysis, we have Fibonacci number has this equation. We are not going to discuss how we derive this equation. If you're interested, you can search on the internet how you can derive this equation. Anyway, this phi here is the golden ratio. And you can put this number here, and you can get the Fibonacci number h. And when we put this number into this equation and solving this relation, then finally we could say NH equals to Fibonacci number h plus 3 minus 1. And when we insert this equation to this equation, then this is going to be like this. And because this number is smaller than 1, when we multiply these several times, it's going to become 0. So we can ignore this part when we are approximating this number. Okay, so this is the detailed analysis of the smallest number of nodes of an AFL tree. So finally, we could say h is smaller than 1 times 4405 times log n plus 1. So this one is tighter bound than h is smaller than 2 times log n, right? So up to this point, we calculated the time complexity of an AFL tree. And from now on, we're going to have a look at how we maintain the height balance. So when we are inserting new items or deleting some items from a binary search tree, the balance might not be maintained. And from now on, we're going to talk about how we can rebalance a binary search tree so that we can achieve AVL trees. As I told you, performing 2 operations, trees could become unbalanced or imbalanced. As I told you, we add a new mapping. We need to find the right place to insert a new node. Then we reach an empty subtree. So when we are replacing a mapping, the tree balance is maintained. So we do not need to think about this case. However, when we add a new mapping, we reach an empty subtree and create a new node, W. The height of all subtrees that includes W may change. And another case that the balance is not maintained is when we're removing a mapping for K. We first call the find method. And if the node is a leaf or has only one child, we just remove the node. This is what we saw in the last lecture. Otherwise, we instead delete the leftmost node in the right subtree. So this is just a recap of what we did for BST. And let W be the node deleted. And the height of all subtrees that include W may change. So when we are adding a new node or deleting a node, W, then we need to think about all the subtrees that include W because their heights might change. And how do we maintain the balance? We're going to do something called restructuring. Let's define some variables first before we talk about restructuring. Let's say Z is the lowest ancestor of W that is now unbalanced. And let's say Y is the child of Z with larger height. Z is unbalanced, so the children of Z must have different heights. So we are going to call that child with larger height Y. And let's say X is the child of Y with larger height. If two children of Y have the same height, then choose the right child of Y. So after we define these three variables, the imbalanced case can be divided into these four cases. So Z is the lowest ancestor of W that is unbalanced after some operation. The operation could be either adding or removing. And Y is between these two children. Y has larger height. And X, another child with larger height. However, X could have the same height as T1. So anyway, we have these four cases. However, case 2 is the mirrored case of case 1. So if you mirror case 1, then we can reach case 2. So in fact, we have technically two cases. However, if we divide it, if we differentiate the mirrored case as a different one, then we have four cases. And when you have a look at this case 4 and case 3, if you mirror case 4 or case 3, you can get the other part. All right, so anyway, in conclusion, we have four cases and we need to deal with these four cases by restructuring. For case 1, we perform something called left rotation about Z. So what does it mean? So that is very simple. We are doing left rotation about Z. So Z becomes the child of Y. And the left child or left subtree of Y becomes the right subtree of Z. And because all the nodes have larger values than Z, because it is on the right side, it was on the right side. And because the values of T1 are larger than Z, we can put it on the right subtree after left rotation, like this. Okay? So this is how we are going to maintain the height balance. So we need to check whether the left rotation maintains the BST property. And as I told you, all the values of T0 are smaller than Z, and all the values of T1 was originally larger than Z. So even though we put it here, T1 here, it doesn't really matter. The binary search tree property is maintained. And you can have a look at the T2 and T3 as well. And you can find it easily that the binary search tree property is maintained. And let's check if the left rotation rebalances the tree. So the height of T2 was larger or larger than or equal to the height of T3. So this one is larger than or equal to T3 because this was originally a AVL tree. Furthermore, the tree was originally balanced. The height of T2 was larger than the height of T3, and the difference is not larger than 1. So HT3 is larger than or equal to HT2 minus 1. The height difference was not larger than 1. And let's say X to be the child with larger height, X to be the height with the larger height, and the height of HX is because we have T2 here, and we have one more node here. So if we add 1 to the height of T2, then that is going to be the height of X. Okay, so height of X is HT2 plus 1. And this one, because we chose that X has larger height than T1, so the height of X is larger than HT1. And because the difference was no larger than 1, HT1 is HX minus 1. And when you have a look at this equation, you can easily verify that HX minus 1 is HT2. And before the left rotation, T0, the height of this one, was height Y minus 2, which is height of H2. Why we need to remove, why is the height difference 2? Because it became unbalanced, because that's why we are considering this case. And the maximum height difference in an avial tree that could occur is 2. Because the maximum height difference in an avial tree is 1. And when it becomes 2, we just do restructuring. So the maximum height difference becomes 1 again, 1 or 0 again. So the maximum height difference cannot exceed 2, even though it is not balanced. So we do not need to think about the height differences of 3, 4, or 5. We don't have to think about these cases. Okay, so that's why the height of T2, T0, is height Y minus 2, which is height T2. And after the left rotation, X is still balanced. And Z, let's think about Z. And height T0 plus 1 is the height of Z, because the height of Z is height of T0 plus 1 node, Z. And you put these equations into the last relation, then height H2, T2 plus 1, which is HT1, is larger than HT2, which is HT0. And we could conclude that the height difference between the left child here and the right child is no larger than 1. Okay, so you could calculate the height of Z like this. And you could say that the height of Z is between HX plus 1 and HX. So you see the height difference between Z and X is not larger than 1. So think about these relations on your own after class, and you could easily come up with this conclusion. So at the first glance, this might look complicated. However, I'm sure that you can understand this part. Okay, let's move on. And for the case 2, because it is the mirrored case of 1, you perform the right rotation about Z. So in this case, this is an example. When we add a new node, it looks like this. I'll give you some time and try to identify X, Y, Z nodes from this figure. I'll give you about 1 minute and send your answers to me. right? The X node is 2, Y node is 4, and Z node is 8. Because Z is the lowest ancestor that is unbalanced. So this was our W. And when you have a look at this node, this one is balanced. And you go one stage up, one level up, and have a look at this ancestor. And this one is also balanced, because the height difference between the left part and the right part is not larger than 1. So you go one level up again here. And when you have a look at this node, the height difference between the left part and the right part is larger than 1. In fact, it is actually 2, right? So we can perform right rotation like this, and the height is balanced. Okay, so this is a concrete example of right rotation about Z. So you can see this Y node becomes a new root here, and Z becomes the child of Y, like this. And for the cases 3 and 4, the question was 4 goes up one stage here, and it goes down here. And this one becomes the child of 8, like this. And the height is balanced. So as Haynes said, Y goes up one stage, and that has an effect of reducing the height because Z is going down as a child of 4. All right, for the cases 3 and 4, we perform double rotations. So this was case 3. And when we rotate X once, and it goes to the right part, and as you can see here, this one is very similar to case 2. Okay? So we can perform this rotation as we did in the cases 1 and 2. So the cases 3 and 4, we can perform double rotations, and we can rebalance the tree. And we are going to implement these avial trees from now on. Before we move on to implementation, any questions? Okay, let's implement avial trees. In fact, avial tree is an extension of a binary search tree. So this was the code we had for binary search tree in the last class. And we're going to modify some of these parts. Sorry for that. I need to delete some programs. Anyway, we are going to modify the implementation of binary search tree to implement avial trees. We need to add one more attribute here. We need to keep track of the height. So that's why we are adding the height attribute here. So self height is going to be the height. And we need a way to calculate the height. So we are going to implement 2 methods, left height and the right height. So we're going to use these 2 methods to check whether some nodes are unbalanced And as I told you, we are going to return -1 if self left is none. Else, we are going to return the height of the left node. We are going to do the same thing for the right height. And because we are adding new nodes or deleting some nodes in the process of using Abel trees, we need to recompute the height of each node several times. So we're going to implement this recompute height method. This one returns true if a node is unbalanced. Okay, so what we are going to do is calculate the left height and calculate the right height like this. And the height of self is going to be the maximum value between the left and right plus 1. Plus 1 corresponds to self. And we're going to return if the difference between the right subtree and the left subtree exceeds 1. So this is how we are going to implement recompute height. And another method that we are going to add is going to be rotate left. And this is going to be today's first PPP exercise. Think about how you can implement this method